I'm the act after lunch where you're all sleepy, so sorry about that. This talk is about Redis. So don't let it fool you that it says it's about persistent memory and that I'm holding a persistent memory module here. It's about Redis, and it's about applications that are going to benefit from persistent memory, like Redis. So I just wanted to make that really clear. I'm Andy Rudoff. I work at Intel. I'm in the data center group at Intel. I'm not in marketing. I'm an engineer. I actually sometimes write code, although mostly now I just tell a bunch of other people to write code. But I've been working on this project related to persistent memory now for years. It's one of the longest projects I've ever been on in my career, but I think it's also one of the most disruptive projects I've ever been on in my career. I'm actually really excited about it, where we're going to take it. And I'm now, it's particularly exciting now that I'm starting to see the actual hardware in use. We're not shipping this yet, but clearly we have samples, and we're working with a lot of partners preparing for when this product ships, including Redis Labs. So you're going to hear a lot about that in this talk, and I'm going to try and give you an overview of what this is and why I actually find it so exciting. So in my career, my kind of unfortunately very long career, or maybe fortunately, as I'm getting older, I've really seen this progression of latency come down from hard drives to SSDs and more recently to PCI Express SSDs. And you can see how the bandwidth, of course, has done sort of the same thing, increasing from hard drives to SSDs to PCIe SSDs. And as these things get faster and faster, they sort of meet in the middle with this technology called persistent memory. And it's actually, there's kind of a long timeline of memory technologies. If you kind of think about back in 1947 when Redis ran on tubes, and how we've kind of progressed. And these technologies came out every few years, but then there was a pretty good gap before NAND flash showed up. But NAND flash happened, during my career, and we all thought, well, that's really cool, and suddenly we could make these really fast disk drives. And then there was another really long gap after NAND flash. And then in 2016, Intel and Micron together announced this 3D crosspoint technology, this new memory. And there are a few other memory technologies like that if you just Google it, you can find out what they are, being announced by other companies. But I work for Intel, so I'm going to talk about the Intel one. So now we're starting to see, what should we do after this long hiatus here? What should we do with this new technology? We're trying to see what we can do with it. So Intel's, like I said, it's called 3D crosspoint. It's a new type of memory. It is persistent. So unlike DRAM, it holds its contents even when you turn the power off. It's large capacity. Since it's memory, you can treat it like byte addressable. You can dereference a single byte of it and go look at those contents. Now, this is one of those slides where it's clear that I'm not the marketing guy. I've taken information that has been publicly released. Not all the details are publicly released. So this is the stuff that I knew was safe for me to say because I could find it with Google, right? So what Intel has said so far is that there's 6 terabytes of this stuff available on a 2-socket system. So 3 terabytes per socket of this is the kind of capacities we're talking about. And that little fact alone, I think, kind of shows you why I'm kind of excited about it, because right now to build a 3 terabyte per socket system is pretty much impossible with DRAM. You'd have to have DIMMs that are not available yet in capacities that aren't available yet. And even if they were, they'd be very expensive, right? So I think we're going to see this explosion in capacity of memory in these systems, and that's pretty cool. It's socket compatible, so you can take this machine that has these DDR4 sockets, and you can put this persistent memory in some of the sockets. This last year was kind of interesting because now that we have samples, we've been doing demos with partners, and you can find videos of these demos online. At SAP Sapphire, SAP demonstrated their database, their in-memory database, HANA, running on top of these modules that I'm showing right here. At Oracle Open World, we saw Oracle running their database on top of persistent memory. So that was pretty exciting, and you can go look up the demos if you want to see the details. Cheaper than DRAM. So again, Intel hasn't announced the actual pricing yet. They have a timeline that the marketing guys do that with, and they certainly don't let engineers like me disclose that kind of information. But cheaper than DRAM, so that was my point about making a 6 terabyte system. Now that actually brings it into the realm of not extraordinarily expensive because you're blowing all of your money on DRAM. So far, Intel has said that it's going to be available later this year. I can't give you a more accurate date than that because, again, I don't want to be the guy who's responsible for that. I want to be the guy who's responsible for the fun stuff that I'm going to talk about now. So why am I so excited about this stuff? Why is this even interesting? So what? It's big memory, right? Well, but it's persistent, so it's also storage. It has aspects of it that are like memory. It has aspects of it that are like storage. And so let's just compare this to some of the storage that's available today. And I'm not even going to talk about hard drives or anything like that. Let's talk about the fast stuff. So if I just take a nice fast NVMe Express, that's one of those drives that goes in the PCIe bus. I buy a nice fast one made out of NAND flash today, and I just want to do a single read. I just want to get access to 1 byte of data. You can see where the latency comes from on the bar on the left. It's about, 90 microseconds or so. And the big blue part of that bar is the media. That's the flash, right? So fine, it's still a lot faster than a hard drive, and it's something that we're, really starting to see exploited in things like Redis on flash or in data centers and so on. So this is great. But you can see that like the green bar down there, that's the link, the PCIe part. The driver's a little red stripe below the green bar. You can probably barely see it. So I'm an operating systems guy, and I'm thinking, I want to make this faster. I could go make the driver twice as fast, and it wouldn't make a bit of difference, right? The driver's that little sliver. It's the media that's taking all the time. And so those little stripes at the bottom really aren't that interesting, and we really haven't spent a lot of time, honestly, messing with those stripes on the bottom because the media is the dominant part of the latency here. But now with 3D Crosspoint, the same stuff that I'm talking about, the 3D Crosspoint media has been out in the form of an SSD now for a good number of months, and that's called the Intel Optane drive. So if I take one of those Intel Optane drives and I do a single read, now I've got that bar in the middle, and you can see the blue part gets way smaller, right? Because now we're in the 3D Crosspoint media. I still have to read 4K because it's a block device. I still have to read it over PCIe. I still have to go through the driver and so on. But now those stripes at the bottom are more interesting because now they're starting to look like they're a little more than half of the latency. So now I do want to try and attack those because the media is no longer the dominant part of the latency. Ooh, a hush falls over the crowd. So that brings us to our motivation to do the thing on the right. Let's take it off of the PCIe bus. Let's take it out of an SSD and pop it right on the memory bus where you can get to it directly, right? So now we're at this picture on the right where you see that tiny little bar, and that's what it takes to just pull in 64 bytes because it's on the memory bus. Things on the memory bus on Intel architecture speak cache lines, which are 64 bytes long. Just to be, apples to apples, I also put a little tiny box over on the end to show you what the 4K read, a full 4K read would look like. But the point about reading 64 bytes is actually kind of cool. If I have a big sparse data structure, like a big hash table or something, and I just want to go read an entry out of it, I probably don't want to read 4K. But with storage, that's my only choice. I have to pull in a whole page, and all that other data is just wasted bandwidth. But with persistent memory, I just access what I want, and I get all that bandwidth back. So this is why I'm so excited about it, right? This is the reason. Because none of this was very, possible before. We couldn't take NAND flash, or we couldn't take hard disk or anything like that and read just 64 bytes. We couldn't put it on the memory bus like this. And like I said, we could mess around with things like the driver and the file system all we want. It wouldn't really make that big of a difference. Now that's not true anymore. Now we want that really direct access I'm showing on the far right. Pretty exciting. So my definition of persistent memory. So what is it? Clearly the thing that I'm holding is persistent memory, but not just this is persistent memory. I wanted to make an industry definition. And without getting into too many formal definitions, what we came up with in the committee where we were trying to figure out how to make an industry definition was it's fast enough that you would reasonably stall your CPU to do a load from it. In other words, a disk isn't persistent memory because it's so slow that you would context switch away and get some other work done while you're waiting for the I/O. But persistent memory is so fast that context switching away is a lot more time than it just takes to wait for the data. So it no longer makes sense to try and get other work done. Everything is just synchronous. You do a read from it, you just wait for the load. Maybe it's not as fast as DRAM, right, depending on the technology, but it's still fast enough, right? So we're still talking about, latencies in the unit of time would be in nanoseconds. It might be hundreds of nanoseconds, but it's still nanoseconds, whereas with disks, it's usually microseconds or milliseconds. So this stuff sits on the memory bus, so a cool side effect of this is that you can DMA to it. Okay, so think about what that means. I can receive a packet from my network into persistence without going through DRAM. Haven't been able to do that before, or at least not since the 40s when they had core memory and old computers. So that's DMA, but what about RDMA? So RDMA is really another cool thing, right? I can actually go and touch somebody else's memory through RDMA. So I can take a value that I want to replicate, and I can write it directly to another machine's persistence, again, without going through, I don't go through their DRAM, I don't even run any code over there, right? I can write something locally, I can use RDMA to write it remotely. CPU utilization on the remote system stayed at 0. Didn't run any code, because it all just happened from the NIC. Ooh, chills. So for persistent memory, that's kind of my definition, but again, why is that valuable? Well, I said some of this already. You can get access to really big data sets that are sitting in persistent memory without imposing a DRAM footprint at all. Today, if I have a big data structure, it's too big to fit in memory, my only choice is paging, right? I have to put it on storage, and I have to pull in blocks to get to it. Every block I pull in has to kick something else out of DRAM, right? So that's a DRAM footprint. But that's not true with persistent memory. I can just access it right in place. I talked about DMA and RDMA. What about the warm cache effect? Well, now that we're talking about terabytes, like 3 terabytes per socket, so 6 terabytes, 12 terabytes, however many sockets you could have many terabytes of data. How long does it take to actually load that up from storage? It actually takes quite a while. And so, if I want to take my machine and just install a security patch on it or something and reboot it to get the new kernel, I don't want to have to load all that back in again, right? It's going to take a long time. Well, I don't have to. It's persistent. It'll still be there after the reboot. So I call that the warm cache effect. It's another one of the values of persistent memory. And again, I've already made the case about byte addressable. Let's talk a little more about what direct user mode access is in a second here. So to set the stage for how you get access to this, I just want to remind everybody what the storage stack looks like. This is like if I were teaching a storage 101 class or something. Here's storage at the 50,000 foot level. I've drawn some applications in user space. They talk usually to a file system. They speak files, open, close, read, write. Sometimes they talk directly to devices. Not that common, but it happens. So they would just open up, /dev/some device and do open, close, read, write, that kind of thing. And then the driver talks to the storage. This is my view of what storage has looked like for quite a while. From a programmer's view, see, I told you I was an engineer. I put code on a slide just to prove it. From a programmer's view, if you're writing C, you would call read or write once you open up one of those files to do I/O to it. And you might be a programmer, you might be looking at this saying, "Oh, I've never called those functions." But if you have done any I/O to a file, somebody's calling those functions for you, right? This is the system call. So even if you're using Java or C++ or some Python or something, if you're doing reads and writes, it's boiling down to these system calls, right? And notice the second argument to these system calls is a buffer. So this is buffer based. You have no choice. You can only read and write to a DRAM buffer. You have no choice. That's the API. It's the only API you've given, right, for doing reads and writes to a file, pretty much. So I call this the buffer-based API. Or is there another API? Well, this is less commonly used, but it's been one of my favorite APIs for a long time. It's called memory mapped files. It's been in the Unix C operating systems for about 30 years. It's been in Windows for about 30 years, so it's actually pretty available, but it's not that common. It's not that popular for probably just reasons of people not really understanding it that well. But you open up the file, you call mmap, and what you get back is this pointer, this base address. Notice I can even close the file at that point. I'm done using the file descriptor. I have the pointer to the actual memory, and then I can use it like a pointer. I can say base sub 0 equals x, or I can stir copy something to it, or I can do a struct copy. The point is I'm doing loads and stores, right? So again, this API has been around forever, memory mapped files. So what is it really doing? Because those files are sitting on disks. Well, it's really just memory mapping the page cache, right? It's really giving you direct access to the page cache. And when I do that first load or the first store, it's going to suspend your process, go bring that page in, and then wake your process back up, and then it can finish the loads or the stores. So it's pretty powerful. You do have to flush things to make them persistent. If you do store, 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 it's not necessarily persistent until you call the flush API, which on Linux is called msync or fsync. But it is pretty powerful. And actually, most of you are using programs that call mmap. You might not realize it, but it actually is used in a lot of places, especially in libraries that do things like memory allocation, such as Redis, which does use the JE-malloc allocator, which calls mmap to get more memory. So I talked about paging, and that's what memory mapped files normally do. But what if I didn't want to do that? What if I don't need to do paging because I have persistent memory? So let's talk about this. So this is the programming model for persistent memory. And you can see down at the bottom there I have persistent memory shown in the system as an NVDIM box. And that really could be a whole bunch of these NVDIMs. These are our modules here from Intel, but there are NVDIMs in the market today. You can buy them today. They're tiny compared to what I was talking about. They're like 8 gigs or 16 gigs. That's tiny, right? 8 gigs. If we drop 8 gigs of memory on the floor, we don't even bend over to pick it up. We just leave it down there. But that you can buy them today. So basically, an NVDIM driver takes ownership of that and exposes it through these different pathways. The one on the left is for manageability, so you can configure it, check its health, and so on. The middle path is kind of this, I'd call it the legacy path. This is for people who don't want to modify their applications. The NVDIM driver provides the common block interfaces, block read, block write. So existing file systems and existing applications, they just work. But of course what happens is when you send down a block operation, the driver is turning that into a mem copy. It's actually turning it into loads and stores. So you get unmodified applications just work. And they just think they're seeing a very fast SSD, the world's fastest SSD, right? But the exciting part's on the right. So on the right, you take a persistent memory-aware file system, and you can use the application on the right can use the normal file APIs, open, close, read, and write, and that works fine, and maybe it's a little faster because the persistent memory-aware file system turns those into loads and stores. But what's really exciting is what happens when you call mmap. When you call mmap, when you memory map the file, you get that far right blue arrow. That far right blue arrow is direct access, direct load store access to the media. Right? This is the shortest code path available, possible. Right? I do a load instruction, and I run no kernel code. I don't take any interrupts. I do no context switches. I am loading from the media, right? Comes right out of the media. I couldn't do a shorter code path unless I predicted that you were going to do that load and crammed it into a register before you asked me for it. That feature, where we skip the page cache and we give you that direct access, has been named DAX by the Linux guys, and believe this or not, the Windows guys picked up the same name. So it's actually called DAX on Windows, too. I don't know how that ever happened. So this is the programming model. Basically, we got a bunch of companies together a few years ago to try and say we should all do it the same way. And we formed this group in SNIA, the Storage Network Industry Association. And we drew a programming model, and look at the picture. Ah, yes, it's the same thing because, lo and behold, I was on that committee and I drew the slide. So it really is an industry standard now, and has been implemented on both Linux and Windows, and I'm actually very proud of that. There's a kind of a quick slide about the SNIA thing, and you can see from the logos there, we had a lot of people involved. Microsoft was there from day one. Red Hat, the Linux guys don't really like these standards committees. Red Hat saw that there needed to be an agreement on how persistent memory worked. They joined SNIA just to join this committee. So we've had a lot of these guys basically meeting every week for about 5 years now. So it's been a long haul. Mostly just to get everybody to agree that memory mapped files make sense, and they do, so I consider that a success. So what's the state of the ecosystem today? The detection of the NVDIMMs plugged into the system, we put that into ACPI 6.0. We're at ACPI 6.2 now, so it's actually been out there for a couple of versions. So that's the thing that causes the NVDIMM driver to load. So that's available and shipping already in a lot of platforms. The stuff in the operating systems, exposing the persistent memory as memory mapped files. The persistent memory aware file systems that I mentioned on Linux, the upstream ones are ext4 and XFS. So both of those file systems support persistent memory today. Shipping, it's actually been upstream for more than a year in both of those file systems. So we got that code into Linux. And I say upstream because there are some file systems that are being written for persistent memory that aren't upstream yet. So in the normal Linux fashion, you're going to have a lot of choice, right? A lot of different file systems to choose from. Windows, the persistent memory file system is NTFS. That's also been shipping in Windows for the better part of a year at least. Optimized flush is a term that I use for being able to flush to persistence without having to call into the kernel. Remember, I told you to make something persistent, you had to call msync. That's fine. You call msync, and what's msync going to do? There's no page cache, right? Traditionally, msync pushes pages out of the page cache. Now what does it do? It just flushes the CPU cache to make sure that the store has made it all the way down to the media. Well, that's just an instruction. The instruction happens to be called CLWB, cache line write back. Well, if I can do that instruction in the kernel, can I just do it from user space? Absolutely. So we do support that in both OSs, and it's faster, right? So you can make writes to persistent faster. There's a couple of other kinds of flush that I'm not going to go into in the interest of time here, but just suffice it to say that the committee is working on the detailed semantics of all these different needs of being able to flush over RDMA or being able to flush to different fault domains and things like that. If you're interested in it, all the specs are online and freely available. But virtualization is pretty interesting. So wouldn't it be nice if that direct path that I mentioned would be available inside of a guest, inside of say a KVM guest? Well, all those changes are upstream in KVM, and so you can do exactly that. You arrange for KVM to start. You tell it what file on persistent memory should look like an NVDIMM inside the guest, and all the same software works. It just thinks it's an NVDIMM, and again, you get that same direct path all the way from the guest all the way to the hardware. The same is true for Zen. The changes are upstream being reviewed still. And the same is true for the other commercial virtualization technologies. They just haven't announced when they're shipping it yet, and so I can't, but they've all announced that they're doing it. So that's another cool part about the ecosystem. The virtualization is basically taken care of at this point. How hard is it to write a program that uses this stuff? I just told you all you got to do is call mmap, right? But that is kind of like walking up to some poor programmer and saying, okay, here's a pointer to 6 terabytes. Have fun. It's not easy programming because then what do? How do you carve it up? What's the equivalent of malloc and free? How do you decide what's in use? And the worst part, how do you decide how to keep the data structure consistent in the face of a program crash or a machine crash? Right? It's persistent. We're used to writing data structures that are volatile, like hash tables and B trees. And so if I'm in the middle of updating one of those data structures and my machine crashes, it's no big deal because all that memory's gone when I come back. It was volatile. But this is persistent. So it's all still in the state you left it in. And if you have a memory leak, what's worse than a memory leak? A persistent memory leak, right? So how do we solve that? Well, we solve that with something called PMDK, the Persistent Memory Developer Kit. PMDK is a menu of libraries, a collection of libraries. It's what we're doing is trying to solve some of the harder programming problems with persistent memory and just put them all out there in libraries without requiring any new compilers. There's no compiler changes, no linker changes, anything like that. And we want to tune this stuff for performance. We want to make sure these are very solid algorithms. And then we've open sourced it. We put it under a nice flexible BSD license. You're free to use the libraries, even in closed source products. You're free to steal code from it. You can hack the crap out of it and put it in your program. We don't care. We're not trying to make money from the libraries. We're trying to make money from the persistent memory, right? So I'm just trying to make it as easy to use as possible. You can see from the picture on the right where the libraries kind of go. And earlier I bragged that was the shortest possible code path in the world. Now I'm putting code back in it, right? But it's shrink to fit. You put in just the code that you want. And if you need transactions, you put in just the code that does transactions. Right now we're up to 10 libraries for various use cases. And they do, the first two things that we had to do are the things that we got the biggest requests for. Transactions, so that your data structures are correct in the face of failure, and a memory allocator. Why can't I just take the malloc that comes with libc and use it? It's just full of assumptions about volatile memory. If I tried to use that malloc and the machine crashed and I came back, the malloc would dump core, right? It would be like, something's wrong, these pointers are half changed and so on. It's just not made for persistence. So we needed a persistent, safe allocator, and that's what we wrote. We have a few tools as part of PMDK, things that tell you if your program's not using persistent memory correctly, like a plugin to Valgrind that tells you if you have a persistent memory leak, for example. And like I say, it's open source. In fact, it's product neutral. So this is kind of an interesting exercise to go through as an Intel employee, and I'm trying to do this stuff to make sure that this Intel technology is as useful as possible. Making it Intel specific and telling people that they would write to an Intel specific API just doesn't seem right? If you want something to be a success, I think it has to be useful across the whole ecosystem. That means, if there's persistent memory in non-Intel products or non-Intel persistent memory, like the NVDIMMs that are shipping today, this stuff should work, and that's exactly what it does. In fact, we accepted changes for ARM a few months ago. Not done by us, but a pull request came in, and of course we reviewed it and accepted it. So it is product neutral, which I hope will make it more successful. So like I say, it is a collection of libraries. There's a list of some of the libraries there. The ones that are red are the ones that are transactional, but some of them are non-transactional because some of the use cases, people don't actually care about the persistence. And that hopefully came out during the keynote talk this morning, that there are cases where you just say, well, gosh, I have 6 terabytes of this stuff in my system. I don't actually care that it's persistent. I just want to use it for its capacity. Well, there's nothing wrong with that, and you still probably want some sort of an allocator. So I'm going to talk about that in a little more detail here. But first of all, the most common library that we have that people are using for persistence is called libpmobj for transactional object store. I don't mean object like a Java object or something. I mean object like object storage. In the storage industry, we talk about object storage where you store things of different varying sizes. They're not block-based. And so you can see from kind of my block diagram of the library here, it has transactions. It has a bunch of these atomic operations, like I said, for allocation and so on. We have some lists and some locks and things like that. It's built on top of an underlying library called libpmem, which does the basics of knowing when you have to flush the cache and things like that. So that's kind of a quick block diagram of how it works. To use it from C, well, C doesn't have a lot of facilities for things like transactions, and I didn't want to modify the compilers because I wanted to make sure this worked with a lot of different C compilers. So we came up with these macros. They're a little funky, but they work. You can see there's a transaction begin macro, and there's a transaction end macro, and those are really the only two that are mandatory. And so if I do tx begin in an open curly brace and I put a whole bunch of code in there, it can do things like allocate, free, change pointers, insert something into a linked list, insert something into a hash table. It can do all sorts of stuff. It can modify 20 megabytes of data. Then I do a tx end. that entire thing either happens or it doesn't happen, right? If the program crashes in the middle, we roll it back, right? So we make the entire thing transactional. And, C doesn't have try, catch, or any kind of exceptions, so we had to do all sorts of macro magic for that. So it's a little ugly to have these macros, but what can I say? We didn't want to modify the language yet. We might do that eventually, but I don't want to sit in committees for about 10 years to what it takes to get something into the C language. So that's kind of just a quick look at what the syntax looks like in C. Actually, just skipping ahead a little bit, just in the interest of time, I'll show you what C++ looks like. Because C++ is a more powerful language, we're able to make it cleaner. So here's an example of taken right out of our website. There's a queue example where we insert something into a queue. You can see the elements are these green elements there, and we're just going to take one of those structs and push it right in there. And you can see what the code looks like here. We have a push function that is going to push it's going to allocate a new member and push it into that queue. And the shaded area, or the area between the red braces there, is the transaction. And so make persistent is a memory allocation. You can see me fiddling around with some pointers there and so on. And there's no new syntax here. This is all just valid C++. If you're not a C++ programmer, you might not know what that weird syntax is with the ampersand and the square braces. Anybody know what that is? Yeah. You know what it is. Good. It's a lambda. It's a nameless function, right? And so those turned out to be really cool, easy things for us to make transactional. So if you hit any exceptions in that function, we abort the transaction. If your program dies, we abort the transaction. And so what happens is you actually end up with some cleaner code, because not only do we handle the case where the program crashed or the machine crashed or the machine lost power, but if you hit any errors in the middle of this stuff, just throw an exception. We'll catch it and we'll abort the transaction for you. We'll roll back all the state, right? So you actually end up with code that has a lot less of these cleaning up after errors because we do it for you. So it actually turned out to be pretty clean. And we're just kind of using the C++ type system here to track what's going on with persistent memory so that we can build the undo log that we can roll things back. So it turns out to be a pretty natural way of programming. Okay, so now let's talk about how does this relate to something like Redis or an in-memory database. So here's kind of the division of responsibilities if you're using these libraries. This is an example of what if we made a version of Redis that used persistent memory to store things persistently. So you can see down at the bottom is both your DRAM and your persistent memory. And Redis would just use DRAM directly, as I'm showing with that left arrow. But on the right, our lowest level library, libpmem, handles detecting, what are the right instructions that are available for flushing, what kind of hardware is available here. It abstracts away the hardware details. It figures all that out. Then on top of that is libpmem that I mentioned before. It creates transactions and gives you transactional allocators. And then so Redis, when it wants to use persistent memory, it uses the path on the right, and that makes it all safe in the face of failure. And so the change to Redis then would be to decide, okay, well, what goes in DRAM and what goes in persistent memory and what goes on storage or whatever, that kind of idea. And notice I kind of drew it as a nebulous app here, but the APIs and the protocols supported by Redis haven't changed. So the app is unmodified, right? The knowledge that there's even persistent memory in the system has only sort of permeated up to the Redis level, but not higher. So everybody just sees a better Redis. They have no idea anything changed. Just, wow, this is better. So that's an example of what we would do if we made a persistent change to Redis. But like I said before, what if we just wanted to use it for its capacity? What if we just wanted to make it volatile? We have a library for that too. We call it libmemkind for different kinds of memory. And what it does is it allows you to have multiple different pools of memory with different performance characteristics. So libmemkind also understands different NUMA nodes, different node socket, node localities. It understands other memory technologies like high bandwidth memory. It basically allows you to have all these different pools of memory. So you could modify Redis to decide, okay, well, I'm going to put this in it's a hot data structure, so I'm going to put it in my fastest pool of memory. And these other things I'm going to put in my more cheaper but larger pool of memory, and so on. And that libmemkind is kind of cool that you can use all these different pools, but you don't have to remember where you got the memory. You don't have to keep all this extra metadata around to remember where you got the memory. It has one free call. So when you decide to free something, you just call the free call, and libmemkind says, I remember this belongs in this pool. So it handles, it keeps you from having to track which pool you allocated things from. So the libraries that I showed here, including libmemkind, they're validated, they're production quality, they're out on GitHub, and actually most of them are in the common distros already. RHEL and Fedora and SUSE and so on. So you'll find them in most distros. We're still figuring out how to get them into some of the distros, since there's always some process involved. So to kind of summarize, as I said at the beginning, this is a talk about Redis. So what would it mean for us to have Redis use persistent memory? So I think there are volatile usages and there are persistent usages. And we started looking at this actually quite some time ago, and we aren't Redis experts, so we just started fiddling around to try and figure out what could be achieved. Like I said, we took libmemkind and we just made a volatile use case. It doesn't care that it's persistent. We just wanted to try having multiple tiers of memory. Then we also used libpmmobj to make a persistent use case where most of the data actually ends up in persistent memory, but some hot things end up in DRAM. And then your memory is already warm on startup, so you can come down, you can come back up, and all the data is still there. So we kind of did these as not production quality, just proofs of concept to see what could be done. We put it all out. It's on our GitHub site. If you go to the pmm.io site, you'll find it all. But of course, we're much more excited now. We've been working, in more recent months with the Redis Labs guys, who are experts on the internals of Redis and actually know better than we do what should be placed in what kind of tier. And so we're much more excited about the results that we're seeing there. But we still publish these things and put them out there to use as examples, not just for Redis, but for whatever your favorite program is. So those things are all available. Okay, so that was kind of the whirlwind tour of persistent memory. Why don't I open it up for questions and see if anybody has questions. The guy with the mic will run right over to you. Thank you. And
hello.
Hi.
Okay, you've successfully infected me with your giddiness. This is really cool. I'm realizing that I have like 30 years of baggage in my head about worrying about serializability and all the layers of cache in the OS in the, you called it legacy path.
Yeah.
Can you help me understand if I have two programs on two different cores, just writing to different parts of PMEM and the system restarts, what kind of serializability guarantees I would or would not have?
Yeah, so
between two registers.
And
two variables.
And thank you, by the way, for using the word serializable, because that is one of the interesting points about how we make things persistent traditionally, right? We serialize them. We encode them in some way, like JSON or something usually much more horrible and complex. But with persistent memory, you could just store these things in native or format. In fact, all of our libraries do that. They store it in the native byte order and the native encoding. We never serialize. But when you start your application up, in the headers of all of our files, we store the ABI information. So if you try and move the file to another machine where the ABI is different, we say, whoa, sorry, size of int is different on this machine or something. So now to answer your question, for 30 years we've had these memory mapped file APIs. There's no assumption by software, correctly written software, that something is persistent until you've called msync. And so that's the same here. So things may or may not have been evicted automatically. They may or may not have made it to persistence, but to know for sure you need a store barrier. And that store barrier is either msync or you doing the equivalent from user space with those flush instructions. And so as long as you write your code that way, you're fine. As long as you say, I don't assume that something's persistent until I've issued my store barrier, you'll get exactly what you're expecting. For multiple cores, it all works. Multi-threaded access. All these libraries are MT hot, by the way, and I've tested with thousands of threads.
Thank you very much.
Sure. Any other?
Yeah, so I guess you said like normally for a single socket, like 3 terabytes would be the limit, but it's kind of common to have like 1.5 terabytes. It is expensive.
Sure.
But what kind of performance hit would we take if we said, oh, we have this 3 terabyte Redis server, we can save a bit of money, switch to your new technology, have it 6 terabyte, but we would take a performance hit. What's the trade-off? We get 50 gigabytes per second from normal DRAM. What will we expect to see from?
So this is a great question. I can only answer it to some level because we haven't released the performance numbers yet because of the progression, the timeline of getting the product to market. Where Intel doesn't release the numbers till they're a little closer to shipping. But a great deal of it depends on how the application has been modified. Which things does it put into DRAM and which things does it put? Because what we found is that most things, it isn't critical that they be at DRAM speeds, but some things it is, right? And so if you just move everything to 3D XPoint, for example, of course the entire app slows down because 3D XPoint is not quite as fast as DRAM. But if you know something about the architecture of your program, and that's why we've been engaging like the Redis Labs guys who know these details about Redis, you can make these choices so that the really important data structures still end up in DRAM. And the things that, well, it turns out they didn't have to be as that fast anyway. So for a lot of use cases, we see little to no slowdown, right? It really kind of depends on the use case, so I can't really say that with a blanket. That was really a very long answer for your mileage will vary. You've got to benchmark it and try different things, and you know.
So maybe you can answer this. Can we expect something like 80 gigabits of transfer? Because that's what we have on the network. Would you be able to saturate that, or maybe not?
As you know, the equivalent of striping on a disk for memory is interleaving, right? So on disk drives, we make them faster by putting a bunch of them there and doing parallel I/O by striping. For memory modules, we do the same thing. We put a bunch of them in the system and we interleave across them. So yes, you can multiply up your performance pretty well. And like I said before, it's already kind of in the same order of magnitude area of DRAM. So that's about as close as an answer as I can get to you.
Fair enough.
I think you get pretty darn close to what you want without me actually having to spill the beans on what the real performance is just yet. It's coming though. It's coming soon. I can't wait until I can spill the beans, actually. So I think we have time for one more question. I see a couple of hands, but.
So 3 terabytes is a lot of space. What happens, what sort of safety features do you have so that we don't lose our data?
Yeah, so that's a great question. It is essentially the same as any other direct attached storage. In other words, if you have a single SSD, I would ask the same question, what safety features do you have? People can mirror it. Of course, I bragged about us not going through the kernel, and a lot of mirroring is done in the kernel now. So we've instead added it to our libraries in library space. So if you actually want to do replication, libpmmobj, our library, will give you transactions where the transaction is not considered complete until it's complete on every replica. And the replicas can be local, like across a couple DIMMs, or they can even be remote, where they go over RDMA. I would say, it's all validated, it all works, but the RDMA thing could be faster, right? Right now it's very synchronous. You make a little transaction and we send it over the wire and wait for it to come back, and that introduces quite a bit of latency. So that's a room for us to improve, right? Maybe bundling those together into bigger, more eventually consistent things right now. So we have some replication in the library is the answer. Now, for something like Redis and a lot of these other programs that are showing up in the cloud, the replication is handled already by the cloud. In other words, they already had to handle the case of, I would just say, a failed module or a failed SSD. It's rare, and they don't like handling it, but they can. So if you just are willing to accept that as that's your solution for durability, then you kind of just live with the chance that could happen every now and then when the module fails. But the 99% case is you don't need the replication. It happens at a higher level. So
just a little bit of a follow-up. So back in the day when I dealt with physical computers, we had like ECC DIMMs. Does this have any sort of error correction built into it?
It does indeed. First of all, it has to comply with the ECC that gets passed on the memory bus. But there's media management, just like there is for NAND, that has a significant amount of ECC around it, absolutely. So that it did actually just count down to 0. So thanks for the questions, and I'll be around if anybody wants to ask questions just one-on-one during the break. So thanks very much.